Okay, this video goes with 2-3. It's our lesson presentation for parallel lines and triangle angle sums. So our goals in this section are to be able to solve problems using the measures of interior angles and exterior angles of triangles. So when we talk about interior angles in a triangle, basically we're saying that the measure of A plus the measure of B plus the measure of C adds up to 180 degrees. And when we're talking about the exterior angles, like we can actually kind of do it like this maybe, or like a pinwheel type shape. Like this, exterior angles. This angle is an exterior angle, and it's going to be equal to the sum of these opposite inside angles added together. So for example, this was 100. These two opposite inside angles would have to add up to 100. We have another exterior angle here. Whatever this angle measures has to be equal to the opposite inside angles on that side of the triangle. So if this was, say, 70 degrees, these two angles would have to add up to 70 degrees. And let's see, exterior. This one should probably go this way. And so this exterior angle here is going to be equal to the sum of the opposite inside angles, which are this one and this one. So let's say this was 60 degrees. These two would have to add up to 60 degrees. So these are the two things we're dealing with in this section. The sum of the inside angles in a triangle have to add up to 180. And the measure of an exterior angle, basically by extending one of the sides of the triangle out, is equal to the sum of the remote, which means opposite, interior angles. So the exterior angles equal to the sum of the remote interior angles in a triangle. Exterior angle up here, the remote interior angles are there. Exterior angle there, the remote interior angles are there. Okay, let's move on. So two parallel lines never intersect, but can two lines that intersect ever be parallel to the same line? Well, I don't think it can, but let's look and see. So here's an example. Draw point P. And then we're going to draw two lines that intersect at P. And they want us to call them line A and line B. And let's say we use a marker. Here's a pencil. Let's say we have a pencil represented by this blue highlighter here, and we put it down parallel to line B, or to line A. And we can see that it's not going to be parallel to B. Now if we rotate it, so that the pencil now is parallel to line B, so we're going to spin it around this way. So now we've got the pencil parallel to line B. We can see that it can't be parallel to line A. So let's talk about this question. Can you rotate the pencil so it's parallel to A at the same time as B? No. Can you adjust your drawing of the two intersecting lines so that you can rotate the pencil to be parallel to both lines? Well, if we try to make the lines almost parallel to each other, this is probably the closest we could get. So here's line P. Let's be A still, and this be B. If we do our pencil, make it parallel to B, we still have to rotate it to make it parallel to A, and we can see that it's never going to be parallel to both of those lines at the same time. So the answer for that is no also. Okay, let's move on. So essential question, what's true about the interior and exterior angles of measures of a triangle? Okay, here we have several different triangles. This is a right triangle. Here we have what we call an obtuse triangle, so it has an obtuse angle, and we call this one an acute triangle. We have an acute, a right, and an obtuse. obtuse triangle, one angle bigger than 90 degrees. Right triangle, one angle equal to 90 degrees. Acute triangle, all angles less than 90 degrees. So we could, say, draw these on a piece of paper, and we could tear off the vertices, tear off the points of the triangle, and we can arrange those so that they basically form a straight line. So 1, 2, and 3 together, if we tore off 1, tore off 2, and tore off 3, and rearranged them, we basically can put them together and see that they add up to make a straight line. And a straight angle measures 180 degrees. So this is a demonstration that the angles inside of an acute triangle add up to 180 degrees. Let's look at the right triangle. Here's angle 6. So we tear off angle 6, we tear off angle 5, we tear off angle 4, we arrange them at the bottom. Here's our 90-degree angle, here's our angle 5, here's our angle 4. They also can be arranged to make 180 degrees, or a straight angle. Our obtuse one, same thing. Tear off the 8, the 7, and the 9 angle, and rearrange them. You can manipulate them so that they make a straight line, which has a measure of 180 degrees. So this is a demonstration that the angles of a triangle sum to 180 degrees. Okay, let's move on. So here's our theorem 210. We've had 9 other theorems in the first section and the second sections. Now we're in the third section. Again, you should be keeping these theorems on a list in order in your notes. So let's see what theorem 210 says. Through a point not on a line, there is one and only one line parallel to the given line. So here's our point that's not on a line. And so here's our reference line. This is the line that we're talking about, our new line to be parallel to. So we're going to draw a line that goes through P that's parallel to B. And we can see that there's one and only one line we can draw that's going to go through P and at the same time be parallel to B. Any other line we draw through P is not going to also be parallel to B at the same time. So line A is the only line that's parallel to line B through point P. So that's our theorem 210. We have another theorem, theorem 211, the triangle sum theorem. The sum of all measures of a triangle is 180 degrees. Now for the proof, they say, see example 2. We can prove this pretty easily, pretty quickly, hopefully. Let's construct a parallel line through C. And this line is going to be parallel to the line that goes through AB. And we have parallel lines now cut by a transversal. So let's number these angles 1, 2, and 3, and 4, and 5, and see what we can do with this. Okay, so by alternate interior angles, we can see that angle 1 and angle 4 are congruent to each other. So let me make a note of that. Angle 1 is congruent to angle 4. And this would be alternate interior angles are congruent. Okay, let's see what else we can do. Let's pretend, let me get rid of the markup I just did, and let's do this a different way now. Let's do the z going in the other direction, like this. Now, here's parallel, parallel. 3 and 5 are alternate interior angles. So 3 is going to be also congruent to 5. So let's say that angle 3 and angle 5 are congruent. And that's the same reasons. Alternate interior angles are congruent. So what we have here is, let me get rid of this markup. What we have here then is that angle 4, which is the same as angle 1, plus angle 5, which is the same as angle 3, along with angle 2, makes a straight line, which means they add to 180 degrees. So that's the demonstration that the sum of the inside angles in a triangle add up to 180 degrees. And example 2, there's a proof of that. Okay, let's move on. Example 2, we want to prove the exterior angle theorem. So let's look at this argument. It's pretty much what I just went through, I think. Draw a line through C that's parallel to AB. And from that, we can get that these two angles are congruent because of alternate interior angles. These two angles are congruent because of alternate interior angles. And we can see that 1 plus 2 plus 3 make a straight angle, which is 180 degrees. So this is the proof down here. These are the steps that go through down there. So I encourage you to look through that more carefully if you don't see what's going on with it. Example 3, we want to use the triangle angle sum theorem. So let's see what we can do with this. This is similar to what was on the mathematical literacy page. So the sum of the angles in a triangle have to add up to 180 degrees. So in triangle TQS, the measure of Q plus T, notice there's T is actually this big angle, plus S needs to make 180. In triangle QRT, 57 plus Y plus this angle RTQ would have to add up to 180. And in triangle RTS, this 78 degree angle and the 32 degree angle and angle X also need to add to 180 degrees. So in each one of these small triangles, the sum of the angles inside need to add up to 180. And in the big triangle, the sum of the angles at each vertex need to add up to 180. So let's see what we can do here. Using triangle, they got their work over here, but let's do triangle like RTS. We've got 78 plus 32 plus X has to equal 180. 78 and 32 is going to be 110. So 110 plus X equals 180. And take away 110 from both sides, X is equal to 70. So in this one, X would be 70 degrees. 70 and 78 and 32 adds up to 180. And on this triangle, we don't really know what this angle here is, but if we look at what else is going on, this Y and 78 degree angle make a linear pair. So we can say that Y plus 78, since they're a linear pair, they have to add up to 180 degrees. And Y is going to be 102 when we take 78 away from both sides. So we can find out what X is, and we can find out what Y is inside of the triangle. Okay, let's move on. Our theorem 212, 212, the triangle exterior angle theorem. The measure of each exterior angle of a triangle equals the sum of the measures of its two remote interior angles. Okay, so this kind of works out like this. the proof is going to be exercise 13, but here's kind of how the argument goes. Let's see. These angles all have to add up to 180 degrees. So 3 plus 2 subtracted from 180 is going to give us the measure here. So this is really 180 minus the measure of 3 plus 2. So here we're talking about the angles 3 plus 2. Over here now, these two, let's change colors. Try this. So now, so that's using the inside angles. But now these two angles are a linear pair. So angle 1 plus this angle, which we saw was 180 minus the measure of angle 3 plus the measure of angle 2, also has to equal 180. So let's see what we can do with that. We can take 180 away from both sides. So we have 1 plus minus measure angle 3 plus measure angle 2 equals 0, because we took 180 off of both sides. So 1 minus the measure of angle 3 minus the measure of angle 2 equals 0. Let's move these to the other side. We have 1 equals the measure of angle 3 plus the measure of angle 2. So the measure of angle 1 should really be measure angle 1. So the measure of angle 1 is equal to the measure of angle 3 plus the measure of angle 2. Measure of angle 1 is equal to the sum of the remote interior angles. So again, using triangle sums, 180, take away these two angles, has to be this angle here. But these two angles have to add up to 180 because they're a linear pair. So when you set that up, the measure of angle 1 plus the measure of 180 plus 180 minus the measure of angle 3 and 2 has to equal 180 because they have to add up to a linear pair. When we simplify, we get a 0 on this side, and we got 1 take away measure of angle 3 plus measure of angle 2 equals 0. Plus measure angle 3, measure angle 2 to both sides. Which cancels these out here and moves them over there. We end up with 1 equal to 3 plus 2. So that's the argument or demonstration that goes with this theorem. Let's move on. Here we want to apply the exterior angle theorem for example 4. What's the missing angle measure? These two angles have to add up to the exterior angle. So the plan would be, if I want to find out what this angle is, I could add these two together and find the measure of angle 1, and then subtract from 180, and that's going to be the measure of the missing angle since these are a linear pair. So for part A, we're going to say 75 plus 45 equals equals 1. And we'll circle it because we're talking about the angle 1. And 75 and 45 is 120, is equal to 1. Together, these are a linear pair, so 180 minus the measure of 1 is going to be the measure of the missing angle, but the measure of this angle 1 is 120 degrees. That leaves 60 degrees for the measure of the missing angle. And if we check, these angles add up to 180. Now let's look at B. This is 109. So let's call angle 2x. So this 109-degree angle is equal to the sum of the remote interior angles, which are 51 plus x. So we can write 51 plus x equals 109. Take 51 away from both sides. X is going to be 58. If we check it out, so x is 58. Now 58 and 51 add up to 109. If we need to find out what this angle is here also, now we could do a linear pair with 109. If we do 180 take away 109, we get 71 degrees. Now if we check it, 71 plus 58 plus 51 should end up to 180. 8, 9, 10, carry the 1, 8, 13, 18. They do add up to 180. So these are the two ways we can basically use the exterior angle theorem. If you get a missing inside angle, you're subtracting the one that you know away from the exterior angle measure. If you know the two inside angles but you don't know the exterior angle, you measure the two, or you add the two remote interior angles, and that's going to be what the exterior angle has to equal to. And if you need to, you can find out the adjacent one, because they are a linear pair and have to add to 180. Let's move on. So here we want to apply these triangle theorems. So Jada made a sketch of her design. The longest sides of the two largest triangles have to be parallel. What's the measure of angle 3 got to be? So they want us to find out what this measure of angle 3 is. So let's see what we got. These are parallel lines. Okay, so kind of paraphrasing what they did, notice that this line and this line are parallel. So by exterior angle theorems, this 50-degree angle and this angle 1 are congruent to each other. So angle 1 measures 50 degrees. We take off the z here. So those two angles are equal to each other. Also, now this is a little bit harder to see, but they bring it out in the description here. If we let me change colors up. If we look at this angle here, this is actually an exterior, one of the exterior angles of this triangle on the right here. This is the outside angle. So these two angles together have to add up to the measure of this exterior angle. Now this exterior angle is the measure of 2 and 85 degrees. So let me write that down. So the measure of angle 2 plus 85 degrees, which is this exterior angle right here, has to equal the sum of these two remote interior angles. And we found that angle 1 is 50 degrees. So these add up to 130. And we've got measure angle 2 plus 85 equals 130. Take 85 away from both sides. Measure angle 2 is going to be 45 degrees. So we can find out that angle 2 measures 45 degrees. Now, next step, since angle 2 is 45 degrees, and the other angle inside this little triangle is 90 degrees, altogether these three angles have to add up to 180, so we can do 45 and 90 and subtract from 180 and find out what angle 3 has to measure. So let me get rid of the markup. So now we're just dealing with this triangle right here, and what we have is 90 plus 3 plus 2 has to equal 180. That's the triangle sums. But we found out that the measure of angle 2 is 45 from what we did over here. And we've got 90 plus 45 plus measure angle 3 has to equal 180. 90 and 45 is 135 plus measure angle 3 equals 180. Take 135 away from both sides, we got measure angle 3 equals 45 degrees. So we can find out the measure of angle 3 is 45 degrees. Okay, let's move on. Let's look at, here they're just finishing it up, and they're solving that it's 45 degrees. Concept summary. The sum of the measures of all the angles in a triangle add up to 180 degrees. And the other idea that we have, or concept that we have, is that the exterior angle of every triangle, and every triangle has 3 exterior angles. If we kind of do like a pinhole shape, like extending out this way, we're going to extend up this way, and then we could extend down this way. One at each vertex. There's an exterior angle going this way, and then also in the other direction. But whatever these angles measure, they're equal to the opposite inside angles. So this angle 1 is equal to the measure of angle 3 plus angle 2. Now we had an angle 4 here. This angle here, let's call this angle 5, would be equal to the sum of 3 and 4. If we call this angle 6 up here, this angle 6 is going to be equal to the sum of angle 4 plus angle 2. So exterior angles are always equal to the sum of the remote interior angles. And that's our presentation.